So in this first problem, we want to derive the equation of motion of classical electromagnetism. So the action is given here. What we have here is the Lagrangian density, and F mu nu is defined here as an antisymmetric tensor. So in order to derive the equation of motion, we will use the Euler-Lagrange equation, which is in this case given as so the derivative of the Lagrangian density. So we just picked a given component, so let's say A lambda minus, and we have a sum here, A lambda. Okay. So the first term is 0. Because L only depends on F mu nu, and F mu nu just depends on the derivatives of the A fields and not on the field itself. So this is 0. Now we just need to evaluate the second term then, so everything is equal to 0, so we can get rid of all minus signs and quarter factors, there's no problem. So we want to evaluate this derivative. So we'll start by something a bit simpler. We'll just start by evaluating the derivative of F mu nu rather than F mu nu, F mu nu. So with respect to this sigma A lambda. So this is pretty straightforward. You just look at the definition of F mu nu, and you see that, so for the first term, the first derivative here to be non-zero, sigma should be equal to mu, and lambda should be equal to nu. So this is just a product of Kroneker's delta. So you have sigma mu, lambda nu, and the second term is just the same but with mu and nu inverted. So sigma nu and lambda mu. Okay, so that's an intermediate result. What we are actually interested in is the derivative of F mu nu, with respect to the same quantity here. So we can just decompose it using the sum rule for derivatives. So it's F mu nu, derivative of F mu nu, sigma A lambda, plus the derivative of F mu nu, sigma A lambda, times F mu nu. Now you can check that these two terms are actually equal to each other. So what we have here is actually just 2 times one term, and we can just replace this expression with that, and I will do the substitution of the delta directly. So the first term, so it's delta sigma mu, so we have sigma here, and the second term is lambda, minus, and this is the same but with mu and nu inverted, so sigma and lambda inverted, so lambda sigma. Now F is an antisymmetric tensor, therefore this is equal to 4 times F sigma lambda. Okay, so that's our results. And now we just use the Euler-Lagrange equation here in order to find out the equation of motion. So it's simply, so I get rid of this 4 factor here and this minus sign already, because this is all equal to 0. So we have simply 0 equal d sigma F sigma lambda. And okay, you might know that better. I mean, if we use mu nu, it's a more familiar form. Yeah, so that's it. So that's the first equation of motion of classical electromagnetism. A second one we can derive directly from the definition actually of F mu nu. So F mu nu here, which is an antisymmetric tensor, you can check that so by symmetry, if you so I introduce another derivative, so F, let's say mu nu. By cyclic permutation of the 3 indexes, the sum of the 3 different terms is necessarily equal to 0. That's something you can explicitly check. So I do just cyclic permutations. We have mu here, nu lambda, and the last term is nu f lambda mu. And that's equal to 0. That's something that can be checked quite easily. So we have here the equation of motions. So I mean, the first one is really what you would call the equation of motion. The second term, the second one, in this case, you can call it as a structural equation. It really just depends on the structure of the F mu nu term. So, classical electromagnetism, equation of motions, as you know, they are actually Maxwell's equation. So we can attempt to find a more familiar form of the Maxwell equation by introducing definition for the electric field and the magnetic field. So F mu nu is a rank 4 antisymmetric tensor. Therefore, it means that it has 6, so antisymmetric tensor. So it has 6 independent components. So we can define 3 of them to be electric fields and the 3 other magnetic fields. So the standard definition is the following. So the 3 components of the electric field are defined as such, okay, where I is a Roman, so all Roman indexes are run from 1 to 3, so they are just spatial components. And the magnetic field is defined through, it's defined like that, ijk bk equals to fij minus. Okay. So we have indeed 6 components here, which completely cover all variables, all degrees of freedom of the F mu nu tensor. So now that we have the equation of motion and definition for electric field and magnetic field, we can simply express these 2 equations here in terms of the electric field and the magnetic field. So let's start with the first one. So first one, so there are actually 4 equations depending on nu, the value of nu. So let's just start with nu equals 0, so the temporal components. So we have 0 equal d mu 0. Now in this equation, the term with mu equal to 0 is equal to 0 because f00 is 0 by antisymmetry. So we actually only have special derivative, which I will call I, with the index I0. Now fi0 by definition here is the electric field, the ith component of the electric field. So that's exactly I, which can also be written as 0 equal the divergence of the electric field, which is the most familiar form that you write this equation in classical mechanics. So that's the first term. The second term, let's take nu to be a special component that we call I. So 0 equal d mu f mu I. Now we can decompose mu in 2 terms. So the temporal derivative, so f0i, and a special derivative, which will I call j, fji. Now I can replace these 2 f factors with electric and magnetic field definitions that we have before. So f0i is simply minus ei, and this term here, fgi, if we look at here, is actually exactly that. So epsilon ijk bk. plus epsilon I jk bk is exactly the component version of the following equation, minus dt of the electric field, and that you can recognize as the cross products of the Nabla operator with the magnetic field, which is a second Maxwell equation. So, I mean, I should say that we have considered here the Lagrangian without source, so that's why we get this particular Maxwell equation. Okay, so there's nothing here. It's zero. Okay, so that's all we got from the first equation. We can see what we can get from the second equation. So it's a bit more involved. There are more free indexes. So we can start by taking in this equation 2 lambda equals 0 and see what we get out of it. So 2. If I just take lambda equal to 0, what do I get? So I get 0 f mu nu. And then you remember it was just cyclic permutation of the indexes. So it's then mu f nu 0 plus nu f 0 mu. Okay, equal to 0. If mu or nu are equal to 0, then these two terms will be equal to 0. Okay, so all the terms will be equal to 0. So mu and nu have to be special indexes. So we can actually write them as I and j. I f j0 plus j f 0I equal to 0. And now we can do the substitution for what we recognize here, electric fields, and here is magnetic field. I j k bk. Okay. Okay, for some reason I put the index up, but okay, it's okay. fj0 is ej. And f0i is minus ei, equal to 0. So what you can recognize here intuitively is just the special derivative of the magnetic field, and that you see here it's the cross product of E with the Nabla vector. Okay, so this actually takes the form minus plus E equal to 0. Yeah, so we have now our third Maxwell equation here with that source. And the last one, which if we look at the three that we already have, so this one, and this one, so the last one would be divergence of B equals 0. In order to get that, so we can actually extract it from the second equation. So first, what we did just before is to take lambda equal to 0. So of course now we will take it to be a special component, let's say I, but you still have freedom from mu and nu. It turns out that the only new information you get is when you take mu and nu to also be special component. If you take either one of them to be 0, then you will find information that we already found before. So what we should do then, and that's something you can check, so what we do now is take lambda mu nu equal, let's say, ijk. So the equation in that case is d lambda fjk plus dj fki. Oh, sorry, that's an I. Plus dk fij equal to 0. So we see that it only involves magnetic field. That's jk l I b plus, okay, k a l dj br plus epsilon a jr dk br equal to 0. So you see that it only involves special derivative of the magnetic field. So we're on the right track, of course, for because we know that we expect divergence of B equal to 0. So we can see that if I, j, or k share the same value, or even just two of these indexes, then we will get 0 equal to 0. The only non-trivial information we get here is when I, j, and k have different values. So 1 and 3, 1, 2, 3. So actually, it doesn't matter which one is 1, 2, or 3 because all three terms you see are actually permutation of the three terms. So yeah. So let's just take as an example I, j, k equal 1, 2, 3 and see what we get. Okay, so for the first term here we get, so j 2, 3, L, 1, B, L, plus k is 3, 1, L, 2, B, L, plus 1, 2, L, 3, B, L. Now, the first term here is only equal, is only non-zero when L is equal to 1. V1. The second term is only non-zero when L is equal to 2. And you see you pick the same as the derivative, the same index as the derivative. And 1, 2, 3 in this case. Epsilon 2, 3, 1 is equal to plus 1. Epsilon 3, 1, 2, you put the 3 there, it's plus 1 as well. And 1, 2, 3 is plus 1. And that's what you get. And that's exactly divergence of B equals 0, which is the last Maxwell equation. Now in a case where I, j, so if let's say I and j have the same value, so you see that from this equation, this term here will be equal to 0, and you can check that these two terms actually cancel each other. So the only non-trivial information we get is when I, j, k have different value, and that's the equation we have.